So we learned about MOSFETs, and we saw that the equation has a lot of parameters in it, but it's just a quadratic relationship between VGS and maybe VDS if the device is in triode region, and ID, right? We'll see that actually solving circuits with the MOSFET in them is easier than solving circuits with BJT. So if you've done your practices so far, you will actually appreciate the fact that these are fairly easy to solve at DC, and then even at AC we'll see that MOSFET circuits are simpler. Now let's go through a couple of examples so we learn how to do the analysis for MOSFET circuits. The first circuit is from your slides, and here's an example. The circuit we have is a simple resistor resistor MOSFET circuit. Two power supplies are used to bias the MOSFET. The supply 2.5 volt at the top, minus 2.5 volt at the bottom. We have two resistors, RD and RS, and the gate is grounded, right? So ID goes into the drain, IS comes out of the drain for an N MOSFET. The question says, choose RD and RS such that ID is 0.4 milliamps and VD is half a volt. Okay, and then the device parameters are given as well. So V threshold is 0.7 volts for this device, and mu and C oxide. So this is a fabrication parameter, you know, depending on who makes the device for you, they give you a number that you have to live with it. Is 100 micrograms per volt squared, but W and L are under your control. So L is 1 micrometer and W is 32 micrometers. Okay, so these are the device parameters, and we want to see what ID and what are RS and RD values to keep the device in that given operating region. So first thing we do is that we figure out what is the operating region, right? So we look at VGD and VGS. VGD, because the drain voltage is given, I can quickly calculate it. So it's 0 volt at the gate, minus 0.5 volt at the drain. So this is minus half a volt, right? And considering that my threshold voltage is 0.7, positive 0.7, this is less than 0.7 volts. And VGS, I know the gate voltage, I don't know the drain, the source voltage. So I want to find the voltage here. So this is VS. So what I can notice is that VS is RSIS, the voltage drop across this resistor, above the negative supply. So VGS is going to be 0 for the gate, minus the source voltage is going to be RSIS minus 2.5 volts. Okay. Now the question is that, you know, what is the operating region of this device? The gate drain voltage is less than the threshold voltage, right? So it's either cut off or active, because if I wanted this to be in triode region, or if it was in the triode region, the gate drain voltage and gate source voltage will both be larger than the threshold voltage. And in this case, it's not, right? So what I can do is that I know it's either cut off or active. If it was cut off, IS would be 0, but I want an IS that is non-zero. ID and IS are equal. So the device is an active region, right? And if that's the case, then ID or IS is equal to half mu NC oxide W over L times VGS minus VTH squared. Okay? So I have these device parameters. I know VTH and I know ID. The only thing remaining is to figure out VGS from this equation. So from here I can see that VGS minus VTH squared is going to be the current 0.4 milliamp divided by 1/2 mu NC oxide is 100 micron per voltmeter, so times 100 times 10 to the minus 6 times W over L ratio, so that's 32 over 1. Okay? And if I do the calculations, I can see that VGS minus VTH squared is so therefore VGS minus VTH. Now it's a quadratic equation. I have two potential answers, plus and minus 0.5. Or my VGS is going to be plus and minus 0.5 plus VTH, so it's VTH plus and minus 0.5. Which one is the correct value? Well, I know the device has to be in active region, so VGS has to be larger than VTH. So VGS minus VTH minus 0.5 is obviously not the answer. So if I go and maybe write that down, I will have two possible answers for VGS. One is 0.5 plus 0.7, so that's 1.2 volts, and one is 0.7 minus 0.5, that's 0.2 volts. Mathematically both of them are okay, but this VGS, the bottom one, is less than VTH. This is larger than VTH. And I'm assuming an active operating region because it couldn't be in cutoff, it couldn't be in triode, and therefore this is the acceptable value. So I reject this one, that's the correct value. Now I have everything that I need. If I have a VGS of 1.2, then I can right away see that Vs is going to be minus 1.2 because gate voltage is 0, and I can calculate Rs. So it's minus 1.2 minus 2.5 divided by the current, right? And since I know Vd, I can calculate ID. So sorry, RD. So RD is going to be VDD minus VD divided by ID as well. So it's going to be 2.5 minus, how much was VD? 0.5 divided by 0.4 milliamps. These are in volts, that's in milliamps. So RD is going to be 5 kilo ohms, and RS, if you do the calculations here, is going to be 3.25 kilo ohms. Okay? So, done. Let's go through another example. So in this case, I have a resistive network to bias this transistor, and I want to figure out the operating conditions. So another example. I have this resistive network here at the gate, a single supply in this case. So VDD is 10 volts, RG1 is 10 mega ohms, RG2 is 10 mega ohms as well, RD is 6 kilo ohms, and RS is 6 kilo ohms. Okay, so solve the circuit, that's the question. What that means is that you want to find out the voltage and currents in the circuit. we identify a few important ones, and then everything else can be found from there. The assumptions for the device are that VTH is 1 volt, plus 1 volt, it's a MOSFET, N MOSFET, and mu N C oxide, W over L, again another parameter for the device, is 1 milliamp per volt squared. So we want to solve this circuit, right? Looking at this circuit, there's a couple of easy things we can do. We can immediately determine VG, right? Regardless of the operating region of the transistor, I can calculate that VG very, very quickly. And the reason is that, as we mentioned before, the gate is essentially an open circuit at DC, right? It's a dielectric that is after the gate contact. No DC current will flow through it. It's an open circuit. If it is an open circuit, on the left side of this circuit, I just have a resistive voltage drive. 2 equal resistors connected to VDD. So VG simply is going to be VDD times RG2 over RG1 plus RG2, and the 2 resistors are equal, so I get basically half that voltage at the gate of this device. Okay, so that was easy, and that is going to be there independent of the operating region of the transistor. Now, for the rest of the analysis, I need to make an assumption here. It's a device, nonlinear device. I don't know what the operating region is. There are different equations that relate the voltage and currents. I need to choose one and then verify my assumption, that I need to pick one and then verify my assumption. But because this is an analog circuit, I'm going to assume active. If I assume active, then ID is given by this relationship, 1/2 mu N C oxide W over L times VGS minus VTH squared. Okay, so in this equation, I don't know ID and I don't know VGS. So I need to find equations from the circuit that will help me, basically independent equations that will help me solve the problem. So what if I write a KVL from here to ground? So if I want to do that, if I do that, VG is equal to VGS, the gate source voltage, right? VGS. And then the voltage drop across this resistor, so which is IDRS. Remember that the current through the source and drain are the same for a MOSFET. Okay. And the good news is that I already know VG. It's 5 volts. So I have one equation here in terms of VGS and ID, and one equation here in terms of VGS and ID, independent equations. So I should be able to solve them, and hopefully I'll find a unique answer, right? So this is my system of equations, and then I go and solve it. So let's say I take this top equation and plug it into the bottom one. Plus 5 for VG is equal to VGS, I don't know what it is, plus ID, I'm going to write that equation for it. RS value is 6 kilo ohms, so 6 kilo ohms times ID. So ID is 1/2 mu N C oxide W over L, that's 1 milliamp, so times 10 to the minus 3 times VGS minus VTH is squared. So VGS minus 1 squared. Okay? And then let me just simplify this a bit. So 5 is equal, or maybe, yeah, let's just simplify it like this. VGS plus 6K times half times 10 to the minus 3. This is going to be 3 times VGS. And now I'm going to expand this bit here. VGS squared minus 2 VGS plus 1. Okay? So I have a quadratic equation as a function of VGS. Arrange it, so 3 VGS is squared minus 6 VGS, and then you have 1 here, so that's minus 5 VGS. And then 3 here, and you do subtract 5 from it, minus 2 is 0. Solve this quadratic equation, we will have 2 possible answers. The first one is VGS is 2 volts, and the second one is that VGS is minus 1/3 of a volt. So pause the video for a second. I have 2 possible answers here for VGS. Which one do you think is the correct answer? And why? Well, if you answer this one, you're correct, because in here we assumed active, right? This is assuming active. We assumed the device is in active region so that we could use that equation. So if I'm coming down these calculations, if I assume the device to be active, this is the correct answer, okay, that supports my assumption. Now, with that known, I can go and solve the circuit. If VGS is 2 volts, then the next thing you can do is that plug VGS into this equation and figure out what ID is. And if you do that, ID is going to be half a milliamp. I actually use this one, right? It's a system of equation. You should be able to use either one of those equations to calculate that. And if ID is half a milliamp, then I can go and calculate VD here. Remember, we are solving the circuit, right? So VD is going to be VDD minus IDRD. So it's going to be 10 minus half a milliamp times 6 kilo ohms. And that's 7 volts, okay? And that's all the important nodes in my circuit. I know the voltage at the drain, gate, and source. So VGS is 2, so therefore VS is going to be 5 minus 2, so that's plus 3 volts now. And this is plus 7 volts, okay? So I've solved the circuit. I know all these voltages and currents. If my assumption was right, there is a chance that my assumption of active region could have been wrong, and all these values are not going to hold up, right? So I need to check my assumption. So the first thing I need to do is that, well, first of all, I noticed that I picked this value. So VGS is already larger than VTH. So one of the 2 conditions that I need for active region is already satisfied. So that one is good. And then what about VGD? Well, VGD is 5 at the gate minus 7 at the drain, so that's minus 2 volts. That's less than VTH because my VTH was 1 volt. So active, okay, right? So the gate source voltage is larger than the threshold voltage. Gate drain voltage is less than that. My assumption holds up. And that's it. I've solved the circuit and I've verified the assumption for my operating region. Let's go through one more example here. So in this case, I have a MOSFET that is biased like this. A 1 volt DC voltage is connected to the gate. The source is grounded. W over L ratio is 2 over 0.18. RD is 5 kilo ohms. And VDD is 1.8 volts. And this is obviously ID. Okay? And the question is, what is the current and voltage in this circuit? Now, device parameters are the threshold voltage is 0.4 volts and mu NC oxide is 100 micrograms per volt squared, right? And you have the W to L ratio of the device. Solve the circuit. So Again, we assume active region of operation. VGS is obviously larger than VTH. VTH is 0.4, VGS is 1. And therefore, it's definitely not cut off. So let's assume active. This is our starting point, in most situations. So assume active. And therefore, ID is going to be 1/2 mu n C ox W over L times VGS minus VTH squared. I have VTGS, the gate voltage is 1, source voltage is 0. So this readily solves to times W over L. Okay, and if I do that, I will see that ID is going to be 0.2 milliamps, and therefore VD, I can calculate, is VDD minus IDRD. It's going to be 0.8 volts. So that was fairly easy, right? Check my assumption. Well, VGS is already known to be larger than VTH, from the circuit and how I put the voltage sources around it. VGD, I do a quick calculation, so it's 1 volt at the gate minus 0.8 volt at the drain, so that's 0.2 volts. That is less than the threshold voltage of 0.4, which I have here. So VGD is less than the threshold voltage, VGS is larger than the threshold voltage, and therefore active. Okay. All right? So that was no problem. Easy to solve. Now, the second part of the question says, what if W over L is 4 over 0.18, right? So instead of what we had here, 2 over 0.18, what if we increase it to 4? So initially, this was 2 over 0.18, and now we increase it to 4. Well, the previous calculation wasn't too difficult. We just go back and calculate ID. In this case, twice the width. All the voltage, the gate voltage is the same, so I get twice the current. It's going to be 0.4 milliamps for the drain current. And then I can calculate VD easily. The voltage at the top, VDD minus IDRD, so minus 0.4 milliamps times 5K. And then all of a sudden I have minus 0.2 volts. That's a problem. As I said, in this resistive transistor circuits, regardless of whether it is BJT or MOSFET, you cannot go beyond the rails of your power supplies. If you're using a 0 and 1.8 volt supply rail, all your voltages must be between these two. So there is a problem. Okay? Where does the problem come from? Well, my assumption for active region most likely wasn't true. And if that's not true, what is the other operating region that I can assume? Well, you can assume cutoff, but that's not really very smart because you already know VGS is larger than VTH. So that's a pointless assumption. If you go and solve the circuit, again, you will have a contradiction very soon. So let's assume triode now. Or it must be triode because it's not cutoff, it's not active. Assume triode. And in this case, ID is actually given by a slightly more complicated expression. So it's 1/2 mu NC oxide, so that's time 10 to the minus 4 times 4 over 0.18 times V. Okay? So plug in all the values we have. VGS is 1 volt, so it's going to be 1.11. I'm just going to expand it at the same time. So it's 2.22 times 10 to the minus 3. It's 1.33 times 10 to the minus 3 VDS minus 1.11 times 10 to the minus 3 VDS squared. If you know VDS squared is going to be very small, you can ignore it and have that linear relationship. But at this point, we really don't know, right? So what does small mean? Small means small compared to VGS minus VTH. So if you know this nonlinear term is small compared to the linear term here, you can ignore it, but we really don't know. And it's just a quadratic relationship. So let's just keep it in and then solve. Now, that's one equation that I have. The other equation I need is from the device from KVLs and KCLs. And what I can do is that I can go and write a KVL from here to ground, right? In this case, because I do not have a current source anymore, right? So remember that in the active region, the device behaves as a current source. A KVL across a current source doesn't help me. A current source can take any value for the voltage drop across it. In this case, it is in triode region. It is a resistor, nonlinear resistor, but the voltage and current, the voltage drop across the resistor determines its current. So I can write a KVL from VDD to ground. So if I do that, then VDD is going to be IDRD plus VDS. Okay? So that's this voltage plus this voltage, right? So you go from VDD to ground. And I just have to plug in ID from the top equation into this. So this is a system of equations now, two independent equations. Plug that value in there and solve. And if you do the calculations, what you notice is that ID will have two values. Again, quadratic equation, you get two possible answers. The first answer is 0.3 milliamps. The second answer is 0.1 milliamp. Well, there's nothing suspicious about either one of these two voltages, two currents, right? So 0.1 and 0.3 milliamps, both of them are fairly reasonable. You have to calculate VDSs as well. And if you have 0.3 milliamps, your VDS value will be 0.3 volts. If you have 0.1 milliamp for current, your VDS value will be 1.08 volt as well. Again, there is nothing here that shouts that, you know, this is obviously the wrong assumption, pick the other one. You know, if you had a negative current or a negative VDS or a VDS that was way too large, all of those things could be flags, but it's really not of any of those situations. So I need to dig a little bit deeper in, right? So I need to see which one of these two actually supports my assumption. If I check the triode operating region, what I need is that VGS must be larger than VTH, and VGD must be larger than VTH. You know, I need a channel at both ends. And we said that, okay, so this one you can rewrite it as this. VDS must be larger than VGS minus VTH. And here is why we actually like this second alternative writing from time to time. Because I have values for VDS here in this circuit. I have value for VGS minus VTH. VGS is 1, VTH is 0.4. So VGS minus VTH is 0.6 volts. And knowing that, I can very quickly check which one of these two values supports my assumption. Sorry, this has to be smaller. VDS less than VGS minus VTH. If it is larger, the device is in active region, right? So VDS has to be less than that, so 0.6 volts here. This is the one that is less. So this is the correct answer. And I don't really need to verify it anymore. You just showed that this makes the device in triode. I already know it is not active. I already know it is not cut off. So that's the correct answer, and I've solved the circuit. And that's that, right? So make sure that you practice a number of these MOSFET problems, different configurations and so on. There's a lot of practice problems that were suggested, and I'm going to post the assignment with additional problems for these devices soon. Now, that's basically it for the MOSFET circuits, but let's just spend a few minutes and talk about the complementary structure that we mentioned, the P MOSFET. Well, structurally it is very similar. So I have again a substrate that is N-type in this case, and I've created my doped regions by inverting that N-type into P+, then put down a dielectric and cover that dielectric with a conductive material, right? So this is my gate, let's say source and drain. Very, very similar to what we had for an N MOSFET. And then I do the same thing. I put a voltage source between gate and source, and a voltage source between drain and source, and start with playing with those values to see what happens. So these are two different values, VDS and VGS. And you go through the same sort of experiments, right? So initially nothing happens for small values of VDS and small values of VGS. Nothing happens. You apply positive VGS, nothing happens. Because if you apply a positive VGS here, what you're going to do is that you're going to bring more electrons to the surface, and you don't want that. So you go and start from the other end. You apply negative VGS to this gate voltage. And if you apply a negative VGS, you bring holes to the surface. And if you bring enough of them, you will invert the doping at the surface, and you will get a P channel from the drain to the source. You get your variable resistor, and hopefully eventually a current source as we saw for the N MOSFETs. The major distinction here is that you have to apply a negative gate voltage. So for P MOSFET, as it turns out, the threshold voltage is less than 0. You apply negative voltages to create that channel between the source and drain. And, but the other discussions we had regarding the operation of the device and all that will be very much the same. So, for example, to have the P MOSFET in the active region, so let's just create the table here, right? Let's say, I'm going to write PMOS at the top, and maybe I remind you what NMOS was just below it. So for a PMOSFET, or let me put NMOS at the top so that it helps you recall the situation. In active region, you had VGS that was larger than the threshold voltage to create the channel at the source end, VGD less than VTH to pinch off the channel at the drain end, and ID was 1/2 mu NC oxide W over L times VGS minus VTH squared. Okay? For a PMOS, it's going to be very similar. So for a PMOS, you will have a VGS that has to be large enough to attract holes to the surface and create the channel, but the threshold voltage in this case is negative. So a VGS that is larger in magnitude, but smaller, if you take into account the sign. VGS less than that, and obviously the threshold the drain end should be the opposite. Noting here that VTH is positive here and VTH is negative here. And then if you look at the current it's going to be 1/2. Well, in this case, the holes are moving, not the electrons, so it's mu p for the holes. C oxide is more or less the same. W over L is the same. VGS minus VTH squared. But remember that VGS is now a negative number that in magnitude is larger than the threshold voltage. So V threshold may be -1, VGS should be -2, right? In magnitude it's larger, but because of the sign it's going to be smaller, right? So it's the same equation, same thing as before, it's just the sign that is different. For triode region, for an N MOSFET, we must have had VGS larger than VTH and VGD larger than VTH. We wanted the channel at both ends, and ID was given by that expression. I'm not going to write it here. For a P MOSFET, you need to have VGS less than VTH. Again, in magnitude is larger. And VGD should be the same. You want a continuous channel from the source end to the drain end. And if you go and write the equation for the voltage and current, it's going to be 1/2 mu P C oxide W over L times VGS minus VTH times VDS minus VDS squared. Again, same equation. Now, the only thing to remember is that you get negative numbers here, right? So VGS is a negative number that is larger than VTH, right? So that VGS minus VTH becomes a negative number. And VDS is a drain voltage that for a P MOSFET is less than the source voltage. So the symbol for a P MOSFET is this, right? So source at the top, drain at the bottom, and gate here. Similar to a PNP device. You know, we put the emitter at the top because of how we usually connect the voltages to these devices. In most cases, the drain voltage is less than the source voltage in a regular PMOS, right? So VDS is actually negative. So this is a negative number multiplied by each other. You get a positive number at the output. And then VDS squared obviously is positive, you know, as well. And then finally you have cutoff. This is the easy one where, you know, for a PMOS, for an NMOS, VGS is less than VTH, VGD is less than VTH. You don't have a channel at either end, and therefore ID is 0. For a PMOS, it's a similar situation. You get VGS that is larger than VTH, again with a negative VTH, and therefore ID is 0. For a P MOSFET, source current goes in, drain currents come out, and gate current, you guess it. Okay, so that's the convention for a PMOS. Now, one thing that some books do, and including your textbook, is that to make the equations look the same and keep everything the same, and I don't know, they try to avoid confusion, but I think they make it more confusing, is that they try to, you know, get rid of the negative numbers that you have here and, you know, use the absolute values. So instead of saying that VGS must be less than VTH for a PMOS where VTH is negative, they say that the absolute value of VGS must be larger than the absolute value of VTH, but knowing that both of them are negative numbers. I think that's a bit confusing. It can actually do more harm, especially when you're writing equations and you're trying to solve these systems of equations and you get these absolute values and you bring them out of these equations. For each absolute value sign that you add to your equations, you have two possible answers, right? So it could be a positive one or negative one that gives you the same value. I don't like it, but if you feel it is going to be less confusing for you, you're more than welcome to use it that way, or to get the concepts that, you know, the channel, existence of the channel and all that. If you would like to think about them in terms of absolute values, that's fine. But I'd like to write the equations like this as they are, and just go back to my mind and say that, okay, for a PMOS, I need a negative threshold. I have a negative threshold voltage. I need to go below that in terms of actual value or above it in terms of magnitude in order to create the channel at the surface. But other than that, the entire calculation is the same. The model you use for a PMOSFET is like this. Well, okay, it's actually upside down normally. So this is ID, and this is VGS, and then ID is from one of those equations in the above. You can use the same model for an N-MOSFET as well, but if you've done enough problems with BJTs, you probably can go past this model and start using equations directly on the circuit diagram. So let's do and a couple of interesting points that I didn't mention before. So you hear about CMOS technology, right? So this is a PMOS. We talked about an NMOS. You hear about CMOS technology, complementary metal oxide semiconductor field effect transistors. And what that means is that there are manufacturing technologies that you can create an N MOSFET and a P MOSFET side by side on in the same technology. And what they do is that, well, if you take an N-type wafer, you can only make P MOSFETs on it. Or if you take a P-type wafer, you can only make N MOSFETs on it, right, because of the dopings that you need. But in these technologies, what they do is that they go and create these little wells that, let's say you have a P-type substrate and you create an N well on that P-type substrate, and you make your N-type transistors inside that well, and P-type transistors everywhere also on the substrate. And you create these devices side by side, make connections to each other. Now, in the same technology, you have access to N-type devices as well as P-type devices. Very important both in analog and digital electronics. We'll see that these two devices, if you have access to both of them, they can make your life much easier. And this CMOS is the technology of choice nowadays in electronics, especially in digital electronics. So when you hear about CMOS technologies, that's what they are. And then when you read about these CMOS technologies, as long as you go beyond the very general news items and talk about a little bit more specifics, one thing that people mention over and over is they say it's a, let's say, 42 nanometer CMOS technology, 28 nanometer CMOS technology, or nowadays it's actually 7 and they're moving towards 3. What does that number mean? That number is the minimum length for this channel. So the smaller you make it, if you go back to this equation, the smaller you make it, the more efficient your device will be in terms of getting a known level of current for a given voltage, or a higher level of current for a given voltage. And how is that determined? Well, that is limited by how close you can put the source and drain terminals to each other, right? There is a minimum, technological minimum, where you cannot do lithography beyond that limit. And therefore, you cannot put them, let's say, right now closer than, let's say, 15 nanometers of each other. So that's the limit for L. W, you can make it as long as you want, as wide as you want. Obviously, you cannot go below the minimum for the width of the channel as well. But when you hear about a certain family of CMOS technologies, that's usually what they mean by the length of the channel or the technology. So let's do a quick example here with a PMOS device. And here is the circuit. Single supply. So question asks, choose resistors such that the transistor is in active region. Right, so this is a device that we will probably use as an amplifier later on. We just want to make sure that it is in an active region of operation. The threshold voltage for the device is -1 volt. And mu PC oxide is 1 milliamp. Sorry, mu PC oxide W over L, so the entire thing, the technology, is 1 milliamp per volt squared. Okay, so I'm not really restricted by the question on where I want to bias this device and how do I want to bias it. I'll just go and choose something here. So what I'm going to do is that I know that for active region, VGS has to be less than VTH, negative threshold voltage, and VGD has to be larger than VTH, right? Or alternatively, VDS, if I want to write it, so I'm going to write it this way. So VGS minus VDS is larger than VTH, or I can write it in terms of VDS, right? So VDS has to be less than VGS minus VTH, okay? So what is important here is that VGS minus VTH value. I want to choose a gate source voltage minus VTH that is, negative. VGS minus VTH must be negative. And then I choose my drain source voltage after that. So let's pick a convenient VDS here. I'm going to say that let's just choose VGS minus VTH to be 1 volt. Arbitrary, right? It's arbitrary. It has to be minus 1 volt because it's a PMOS. And then right away I get a VGS that is minus 1, VTH is minus 1, so it's minus, so minus 1 you have on the left side, bring it to the right side, it becomes minus 1 again. Okay? And I know the source voltage. Source voltage is 5. It's directly connected to the positive supply. So VG minus 5 is minus 2. So therefore, VG is 3 volts. Okay? If VG is 3 volts, I can go and choose RG2 and RG1. So RG2 over RG2 over plus RG1 times 5 must be 3, right? Why? Because IG is 0, right? So therefore, I only have a voltage divider between these two resistors. If this was a BJT, I couldn't do that. And then I choose a criteria for, let's say, the values of RG1 and RG2. Let's say I don't want the current through them to more than 1 microamp. So if that's the case, then RG1 plus RG2 should be 5, the sum of them, divided by 1 microamp. And right here you get an RG1 and RG2 values from that equation. So RG2 is going to be 3 megohms, and RG2 is going to be 2 megohms. Sorry, RG1 is going to be 2 megohms, and RG2 is 3 megohms. Okay, so I've established my gate voltage. What about the drain voltage? Well, okay, so with the chosen value, this is a choice I made because the question let me decide on that. I can calculate ID. ID is going to be half mu PC oxide W over L, so that's 1 milliamp, times VGS minus VTH squared. I chose it to be minus 1 squared, and that is going to be half a milliamp. Okay? And with that value of half a milliamp, I already know my VDS, right? So VDS, I choose it to be, let's say, 3 volts, right? And if that's the case, what I get is RD is going to be 3 volts divided by half a milliamp, which is 6 kilo ohms. Okay? And what that 3 volt, the choice of that 3 volt will give me about 1 volt of swing value. You know, I can increase the voltage at the drain to 4 or drop it to 2, and the device still will be in active region. We'll talk more about that in the amplifier design section, but that's again an arbitrary choice. I could have put it at 2 volts or 1 volt or even 0. You know, I could have chosen an RD of 0 if it was up to me. But anyway, so that's that for our MOSFET analysis, the discussion on MOSFET circuits. Again, I highly recommend that you solve a good number of problems on your own, in your own time, and then definitely spend some time with the assignments that I will soon post, and you will get basically more options. And that will be it. So the next discussion is going to go to chapter 7 of your textbook, and it's going to be about transistor amplifiers. Now that we know how these devices behave under DC conditions, the next question is that how do you actually use them in order to amplify a signal?